I'm aware that, in a sense, I'm teaching my grandma to suck eggs. Do you know that old expression? It's a North American one. It just means teaching someone who already knows something about it. So I acknowledge that I have a lot of experience teaching chemistry in a number of states, and a lot of experience teaching chemistry teachers across a number of countries. But I haven't actually taught chemistry in Queensland. I've taught it in New South Wales, Victoria, and Western Australia. But there'll be things that you will know about teaching in Queensland, about the context, about the ways in which things are done that I don't really know. But I hope that what I can give you is some overarching principles and ideas that will help to organise the various procedures and things that you need to do. So in terms of planning for teaching, obviously you already know a lot about it. You are currently teaching, you have the skills of developing programs of work, you have a good sense of how it works in junior secondary. So I want to just spend a little bit of time talking and thinking about how it's different in senior secondary, and maybe just sharing a couple of ideas as well. One of the things, and you kind of know this, I'm sure, but this is something I actually tell beginning teachers as well, is that we sometimes think that a detailed, careful written plan will stop us being creative, stop us seizing the moment in the classroom and following the student's interest and so on. But in fact, it's the opposite, that if you've got a really good plan, then you can mentally move the pieces around. If you're just winging it and something happens, it's much harder to actually then be able to actually follow that interest, because you have a particular sense of where you're trying to go, or else you follow too many rabbit holes and don't end up getting where you need to go. So, you know, I probably don't need to suggest it, but planning is really important. It helps to build your creativity and your flexibility, and particularly if you're doing it with colleagues, as I suggested before, because you bounce ideas off one another and come up with really cool, authentic assessment tasks that nobody's ever thought of before, and a whole variety of things around that. So now, you know, we know that planning is required anyway. It's mandated. You need to show your program of work to people within the school and possibly people without the school. You need to be able to demonstrate to students, this is the layout of what we're planning to do this year, these are the assessment tasks, this is when they're due, and so on. So it's required, but I'm saying it's also really good. I would also say, though, the more experienced as a teacher you are, the less detailed your plan needs to be. I ask the students at the university to write very detailed individual lesson plans, not because that's actually what you would do as a real teacher, but because that's an opportunity to demonstrate explicitly to me your thinking. Whereas when you're planning for your own teaching, you only need it for you. So it might be a dot point or something that actually you already know what you want to talk about. In chem education in particular, again, it's much more difficult to wing it, because you need to talk to the lab tech, book the lab, organise what experiment you're going to do, what materials you'll need. If you plan to just stay in the classroom but do a little demo, you need to go to the lab and get the materials ahead of time, and so on. So this is one of the challenges of planning for science teaching over planning for other subject areas, that you know, though obviously if you're planning for teaching in music, you might have to acquire an instrument or bring one along, or there's a variety of things you have to do. But in science specifically, these are the things. Quite often you will have to do risk assessments for particular pracs before you can do them, and so on. So that's part of your planning as well. Accommodations for students with particular disabilities or needs in the activities you're going to do is part of your long-term planning as well. Another piece that you can do is an approach called the curricular emphases approach, and I'll talk about that in a little while as well. Curricular emphases approach is something that I've been teaching about for a while, that I learned about when I was in Canada, that it isn't really huge in the literature yet, but I think it really makes sense and improves teaching. In junior secondary, you're planning for 1 year. So this is my year 8 science program of work. In senior secondary, it's a 2-year program. So even if you're not teaching them for the whole 2 years, and you know, different people have different views on whether it's better to have one teacher in year 11 who follows the class into year 12, or whether it's better to have 2 different teachers. But whichever you're doing, you're planning for 2 years. It's 2 years for the experience of the students. So the planning is for that 2 years. A unit Within that, there might be 5 or 6 per year, 5 to 8 per year units that you'll do, depending on, there'll be some longer and some shorter and so on, depending on how you divide the content up. And that will allow you to cover all of the content in the 2 years. There's some looping around, so concepts that you deal with early in year 11, you may need to re-hit in year 12 so that students can demonstrate their knowledge of them at a higher level, and so on. So it really is quite a complex and dynamic process developing an approach. Within a particular unit, it should really have a storyline. I've used the word storyline. Doesn't mean it's a narrative. Once upon a time, the little physicist went down to the laboratory, or chemist, sorry. It's a story at its essence, sets up expectations at the start. The first sentence of the novel leaves the smoking gun and the body lying on the ground, or whatever it happens to be. Sets up expectations. What's happened here? What's going to happen? What would solve this? The middle of the story complicates that, adds details, adds obstacles to the detective finding out what happened and so on. And the end satisfies those interests, ties up the loose ends, and the story wraps up in some way that's satisfying. A unit should be the same as that. You should, at the start, actually be raising the questions with the students. What's going on here? What are we trying to learn? What don't we know? What do we want to know? And you're probably familiar with KWH, well, KWL and KWLH charts from junior secondary. It's actually a primary connections thing. But what do we know? What do we want to know? At the end of the unit, what have we learned? And how do we know? What are our grounds? What is our evidence for our claim to know? It's quite a nice tool even at the higher level, even though it was developed for primary. But even if you don't use that tool, that concept, that the students at the start have these expectations set up. Hey, by the end of this unit, we will know more about something. In the middle, we complicate it. We add the detail, we dive deeply into it, we process it multiple times so they get a chance to get it deep in their heads. And at the end, in some sense, there's a satisfaction. It's not just, okay, we're done now, here's the test, go on to the next thing. It's, okay, now, hey, look back. You didn't know this 4 weeks ago, now you do. You understand this phenomenon in the world in a new way now. So I think that's quite important, that the units have a storyline, that there's some tension, there's some interest and engagement for the students. And I mentioned already that things will, the structure, the physical structure in when the assessments are, when the units are, when they start, when they finish, around terms and so on, will vary depending on what the topic is and how it links and a whole variety of other factors. Curricular emphases approach, I owe it to my colleague Frank Jenkins, who still is a former chemistry teacher. So he was a chemistry teacher for 35 years in Edmonton in Canada. And then he did a PhD after that and became a teacher educator in what would otherwise have been his retirement. Fantastic guy, and he developed this based on some of the science, technology and society work that had been done before. What we're trying to attend to in science education is society more broadly, as well as the science itself. And so we want students to understand the nature of science. What does it mean to make and defend a scientific knowledge claim? How do we test our claims to know things? This helps with things like understanding climate change, understanding fresh and salt water, and why it's important that we try not to melt the glaciers and put them all into the ocean, and a whole variety of other real world things. The ability to actually understand what is a scientific knowledge claim, to judge the graph that they find in the paper that turns out to have really dodgy axes that have been tweaked to make something look how it isn't, and so on. So they should understand, students should understand the nature of science. They should understand the links between science and technology. And I could do a whole other session on science and technology, which came first, because it's a dynamic relationship, sometimes the science, sometimes the technology. And a lot of the applications of science are into various technologies. So students should have a sense of the ways in which technology and science interact, and they should have a sense of science and society. So not only the science of climate change and how greenhouse gases in the atmosphere scatter infrared radiation so that it keeps it in the atmosphere rather than letting it be radiated off into space. That's the chemistry, the science side. But what should we do about it? There's a number of possibilities. You could have a carbon tax, you could plant more trees, you could use nuclear power or solar or wind or a combination of those. There's a variety of possible social things, right? There's a correct scientific answer about what's going on, but there's a variety of social responses to that. What should we do about human cloning? What should we do about a whole variety of other social issues and ethical issues? So students should have these things. But we can't do all three of these things in every unit. It's too much. It adds on to the crowded syllabus, although I said earlier the syllabus isn't that crowded. It muddies the focus and so on. So the curricular emphases model is really simple. If you've got 5 units across a year, you might have 2 that have a nature of science focus. So it's an emphasis. You're still doing the content, you're still doing everything else you're doing, but you're paying particular attention to the nature of science. You might have a technology emphasis, and so some units will be more related to technology. In chemistry, if you're doing something with materials science, it's probably more related to technology. If you're doing something about gas laws, then maybe the climate change stuff comes in, and that's a science and society emphasis. So do you see how it works? So you might have, across the 2 years, you might have your 10 to 16, probably maybe a dozen units in total. And so you'll probably hit each of these emphases 3 or 4 times. And it means that you're not trying to do everything all the time, but it means that you are attending to these really important social connections of science and philosophical connections of science all the way through. Planning is a dynamic process. I said this already, that you go back and forth, you get new ideas, you see something cool on the internet, you go to a conference and see a cool presentation. This particular class is particularly bright or particularly dull or particularly engaged or particularly disengaged, or has a particular interest, that you have a critical mass of students who are interested in some particular topic, or a new misconception that you'd never seen before arises. You thought you knew every possible way in which students could get the mole concept wrong, but there's a whole new one. How do you actually address that and make sure that the student adopts the correct scientific concept, and so on? So it's always dynamic. Every class is different. That's part of the nature of planning to teach. If you do want to complete the optional assessment task for credit in this course, one of the things that you'll be doing, or the thing you'll be doing really, is looking at somebody else's program of work. I got it from a local Brisbane high school, and then de-identified it. So the name of the school is no real school anywhere. The names of anything in it are not of anyone anywhere, but it is a real authentic program of work from a real authentic school. Your mission is to go in and look at that plan for teaching, what that school has done, why they've done it and so on, the layout, the rationale, and then say, all right, I love these things they've done. These things they've done I would have done differently. I'd love to add more here. I'd like to cut some there. I'd like to use these curricular emphases. And it's a chance for you to demonstrate both the content that you've learned, the new chemistry that you understand now that you didn't understand at the beginning, and the syllabus knowledge, the kinds of things that I'm talking about, your own study of the syllabus, what it requires, teaching in context, EEIs, those kind of new things, making sure that you're able to demonstrate that you can do that. So that's what you'll do if you do the optional assignment. Not everybody will. That's entirely up to you. If you don't do it, just click on that link anyway. It's called Optional Assessment, and it's on the left bar of the Learning at Griffith site. And have a look at the program of work, even if you don't do the assignment on it, just to get a sense of what one looks like, to think about how you might plan in your own teaching and so on. So I would encourage everybody to do that. And I'm very happy to talk further about the optional assessment as we get closer to that.